Today let us first see what is basis of a vector space. A subset B of a vector space V is a basis of V if B is linearly independent and LB equal to V. What is the meaning of LB? Linear span of B. B is a subset of V, the vector space V. B is linearly independent and B spans V, or LB equal to V. The set B with these two properties is called a basis of the vector space V. Okay, you already know the meaning of linearly independent vectors and the meaning of spanning set. Spanning set means LB equal to V, or you can say any vector in V can be written as linear combination of the members of V. See this example. The set B equal to 1 0, 0 1 is a basis of the vector space R2 and it is called standard basis of R2. Why is it a basis for R2? The two vectors are linearly independent. You already know it. If you consider linear combination, put that combination 0, you get both the scalars 0 only. In the previous lecture, you did this example. What do we get from this? A0, B0. It means both these vectors are linearly independent. Only one solution, the trivial solution, is there for this combination. Next, does it span the vector space R2? So consider any member from R2, x1, x2. Can it be written as the linear combination of the members of B? Yes, I can write it x1 times 1, 0 plus x2 times 0, 1. So any member x1, x2 of R2 is written as linear combination of the members of B. It means B spans R2. Okay. So both properties of basis are satisfied here. So B is the basis for V. You can see the solution here also. Next, B equal to 1 0 0 0 1 0 0 0 1 is the standard basis of R3. Same way you can do this example. It is for R3. R is also a vector space. What is standard basis for it? The set of real numbers is a vector space under usual addition and scalar multiplication operations. For R2, the standard basis is 1 0 0 1. For R, 1 only. For this 1 0 0 1. For R3, 1 0 0 0 1 0 0 0 1. Likewise, you can think standard basis for R4, R5, etc. B equal to this set is a basis of R3. Of course, it is not standard basis. Standard basis is shown above. How to prove that it is basis? First thing, you will show that this set is linearly independent. Means the three vectors are linearly independent. How to show that? A times first vector plus B times second vector plus C times third vector. Put that combination 0. After that, you will have homogeneous system of three equations. Solve that. If you get all the scalars 0 only, the vectors are linearly independent. You will get linearly independent vectors in this case. And how to show that it spans R3? Consider arbitrary member of R3. You can take x1, x2, x3. write this as linear combination of the three vectors. C times -1, 2, -3. Okay, now simplify this further. You have three equations in ABC. You will have three equations in ABC. Solve those equations for ABC. If you get unique values of ABC in terms of x1, x2, x3, that means this vector can be written as linear combination of these three vectors. You will do this exercise yourself. You will find that this set B spans R3. Okay, so it is linearly independent as well as it spans R3, so it is a basis. Next example, the set of these four matrices of order 2 cross 2 is a standard basis of M22. You can verify yourself. It is trivial. These four vectors in this set are linearly independent. You can check it quickly without doing the calculations. And any 2 cross 2 matrix can be written as linear combination of these four matrices, right? So this is basis. In fact, it is standard basis. For the vector space of nth degree polynomials, the standard basis is 1, x, x square and so on x power n. You know any nth degree polynomial can be written as linear combination of these vectors, and these are linearly independent also. So it is standard basis of Pn. Next, if B1 is a finite basis of a vector space V and B2 is any other basis of V, then B2 has same number of vectors as in B1. So what is the meaning of this theorem? Number of elements in two different bases is same. Bases can be different, but number of elements remains the same. For example, here, this is standard basis carrying three vectors. This is another basis of R3. It is also carrying three vectors. If you construct any other basis, that will also carry three vectors. So the note follows from it. A vector space may have infinitely many finite bases. However, the number of vectors in each basis would be same as suggested by the above theorem. Okay, so remember this point, it's very important. Number of elements in a basis remains the same. This leads to this very important definition, dimension of a vector space. What is it? Number of elements in the basis of a vector space is called its dimension. So what is dimension of R2? You know one basis for it, 1, 0, 0, 1. So dimension of R2 is 2. Dimension of R is 1. Dimension of Pn is how many vectors? 1x, x square is the standard basis, that you remember, n plus 1. Okay, so if you know one basis of the vector space, you can write the dimension. A vector space with finite dimension is called finite dimensional vector space. So for R2 this is basis, so dimension of R2 is 2. Dimension of M22 is 4. Why? Because we know a basis of it which carries 4 vectors. The standard basis carries 4 vectors. Now how to construct bases from a given set in the vector space? First result is any maximal linearly independent subset of a spanning set of a vector space forms a basis of the vector space. Important result, we will now prove it, rather we will use it in the problems. For example, S is this set given in R2, 1, 0, 0, 1 and 1, 5. It carries 3 vectors. It spans R2. From this you want to construct a basis. So how to do that? Find maximal linearly independent subset. Maximal, you understand? After that, suppose there are 2 vectors which are independent in it. If you add third vector, consider third vector, then it is not linearly independent. Okay, that is the meaning of maximal. So for example, I consider first 2 vectors 1, 0 and 0, 1. These are linearly independent. But if I consider third vector also with it, you will find that now these are linearly dependent. You can check it. Okay. So maximal linearly independent subset is 1, 0, 0, 1. So with these 2 vectors it is a basis. Same way you can consider these 2 vectors or these 2. All these are maximal linearly independent subsets of S. So these are bases of R2. Next, every linearly independent subset of a vector space can be extended to form a basis of the vector space. Consider R2. I am writing a set here, say 1, 0 only. S is carrying only one vector. This is linearly independent. You know that every non-zero vector in a vector space is linearly independent. So this is linearly independent. Does it form basis of R2? No, it doesn't form. So we can add one extra vector to this set to form a basis. For example, I can add here 0, 1. I could add 1, 5 also. I may add any vector here so that this set is a basis of R2. Okay. So any linearly independent set can be extended to form a basis of the vector space. This is called extension theorem in fact. So from spanning set, how to construct basis? Find maximal linearly independent subset. And from linearly independent subset, how we construct the basis? We add extra vectors. In case it is itself a vector basis of the vector space, then it's fine. Otherwise, we can add extra vectors to make it a basis. For example, S is carrying 1, 3, 7 here in R3. It is non-zero vector, it is independent, linearly independent. So we know that dimension of R3 is 3. So basis must carry exactly 3 vectors. So we need to add 2 extra vectors. So you need to choose 2 suitable extra vectors so that the whole set is linearly independent. So here what are added? 0, 1, 0 and 0, 0, 1. You can choose vectors from the standard basis. The idea is that after adding the new vectors, the set is linearly dependent. Okay. This is very important because this gives the whole idea of construction of basis of the vector space. If we remove one or more vectors from the basis set of a vector space, it is no more a spanning set of the vector space. For example, this is basis of R2, you know. What happens if I drop one vector from it? I construct a new set B1, it carries only one vector. Which property of the basis is no more here? It is not spanning set. It is still independent. You know, in basis there are 2 properties. It is linearly independent and it spans the vector space. Because it is non-zero vector, it is still independent. Even I have dropped one vector. But it is not spanning set. For example, if I want to write the vector 1, 2 from R2 as a linear combination of this vector, it is not possible. I cannot write a into 1 times 1 comma 0 for any real number a. Okay, so spanning property of the basis we are losing here. If we insert one or more vectors in the basis set, it is no more linearly independent. So we cannot insert also extra vector. For example, this is basis of R2. If I add say 1, 2 here, insert extra vector, it is no more a basis of R2. Which property doesn't exist now? It is no more linearly independent. You can clearly see that 1, 2 can be written as linear combination of 1, 0 plus 2, 0, 1. So one vector in the vector space is linear combination of the other two. Okay, that means B is not linearly independent. So idea is that if we remove one vector from the basis, it is no more spanning set. If we insert extra vector in the basis, it is no more linearly independent. Thus, the number of elements in the basis set does not vary, and that we call dimension of the vector space. Okay. If W is a subspace of a vector space V, then dimension W is always less than equal to the dimension of the vector space. In this example, find a basis of a subspace of R4 spanned by these three vectors. A subspace of R4 is spanned by these three vectors. So how to find basis for that subspace, not for R4. R4 is having some subspace that is spanned by these three vectors. Okay? Read this carefully. Find a basis of a subspace of R4. It is not for R4. You know, R4 cannot be spanned by less than 4 vectors. Okay? So here the question is about subspace of R4, which is spanned by these three vectors, and what is required? Basis of that subspace. So how to find the basis from the spanning set? Find maximal linearly independent subset. So first check all the three vectors. Maybe all three are independent. In that case, the three vectors form a basis. So how to check independence of these three vectors? Find RREF, that is the best way you know. So this is RREF, and from this RREF we see that all these three vectors, even you can find REF, that is also fine. So these three vectors are non-zero in RREF. So what does it mean? These three vectors are linearly independent. Already these are given spanning. These are spanning vectors for the subspace of R4. It means the three vectors, this set S forms a basis of the subspace of R4. Okay. And you already know that row vectors of the row equivalent matrix of basis vectors matrix also form a basis. So you consider these three vectors in the basis or these three, it's fine. Okay, because it's simplified span. You get simplified span also by using RREF. So these three vectors are also linearly independent, and these will also form basis of the subspace of R4. Okay, so in this chapter what you have learned mainly, let me go back and revise the main things. The main important definition is real vector space. What is a vector space? See again. A real vector space is a non-empty set V where two operations are defined, plus and dot, plus we call vector addition, dot scalar multiplication. With respect to plus, these five properties are satisfied. Okay. And with respect to dot and plus mixed, five more properties are satisfied. So real vector space means if these 10 properties are satisfied, then V is a vector space, real vector space. After that, you learn some standard examples of vector spaces. Real numbers form vector space under usual addition and multiplication properties. R2 forms a vector space. R3 forms in general Rn forms vector space under which operations? These operations, coordinate wise addition and coordinate wise scalar multiplication. Okay. Next standard example, the set of all n cross n order matrices forms a vector space under usual addition of matrices and scalar multiplication in matrices. Okay. All polynomials of degree less than equal to n form a vector space under usual addition of polynomials and usual scalar multiplication in polynomials. Then set of all functions under usual, all functions defined on 0, 1 under usual addition and scalar multiplication forms a vector space. This doesn't form a vector space. This is unusual vector space. This is not usual. Here R plus is the set of all positive real numbers, and the operations you see U plus V is U into V, and A dot U is U power A. So under these operations, the set of positive real numbers forms a vector space. So this is not usual, unusual vector space. Then some more examples you did of unusual vector spaces. Next thing that you learned is subspace. What is a subspace? Any subset of the vector space which itself forms a vector space under the same operations as in the vector space. Okay. What is important point here? How to check subspace. One way is that you verify all the 10 properties. Other way is by this theorem. This theorem says that if you want to check W as a subspace of V, what to do? Simply verify two properties. W is closed with respect to vector addition and W is closed with respect to scalar multiplication. Means vector, the closure property with respect to vector addition, and you can say closure property with respect to scalar multiplication, both are satisfied. Those verification of those two properties is equivalent to verifying all the 10 properties. Okay. So this is how we check W is a subspace of V. We did some examples on this. This is subspace, but the other two sets are not subspaces. We did these things in the previous lecture. Then algebra of subspaces, W1 and W2 are subspaces of the vector space. Intersection is always a subspace. Union need not be. So remember one counter example for this. Union can be subspace if either W1 is subset of W2 or W2 is subset of W1. Span of a set, it's a very important definition. Again, I'm repeating it. What is span of a set? The set of all finite linear combinations of the members of S. Finite linear combination means linear combination of finite number of members of S. S could be an infinite set. But in the linear span, you will consider linear combinations of finite number of members of S. Okay. So collection of all linear combinations of finite number of members of S gives you linear span of S denoted by LS. So finding LS means simply consider linear combination of all the members of the set S in case it is finite. If it is infinite, then consider linear combination of the finite number of members of S. For simplified span, what to do? Find RREF. What is the advantage of this? From simplified span, sometimes it is possible to know that the span is itself the vector space or not, or some known set. Okay. So span of the row equivalent matrices is same. For polynomials also you can find span in the same manner, means you just write their coefficients and then find RREF. So using this approach you can find linear span, means simplified span. For matrices also you can follow the same approach for finding simplified span. About LS, you may look at this result. LS is always a subset of V, it is always a subspace of V, and it is the minimal subspace of V containing S. The concept of linearly independent vectors is very important. How to check given n vectors are linearly independent. A1, V1 plus and so on, A and Vn. Consider their linear combination, put that this linear combination equal to 0. After that, simplify this depending on the definitions of scalar multiplication and vector addition. If this implies only one trivial solution, means all the scalars are 0, then the vectors V1 to Vn are linearly independent. If you get solutions different from 0 also, means there exist non-trivial solutions, then the vectors are linearly dependent. Okay. Very important definition of linearly independent vectors. So how to check the vectors are linearly independent? Already you have done these examples. Put the linear combination equal to 0 and find the scalars. In case of R2, R3, etc., you get a homogeneous system of linear equations in the variables. So you can apply that RREF approach to get the solution. Two vectors are linearly dependent if one is scalar multiple of other. Single non-zero vector is always linearly independent. Okay, zero vector is always linearly dependent. About two vectors, how to check linear independence? If the two vectors are not scalar multiple of each other, these are linearly independent. If these are multiple of each other, then naturally the two vectors are linearly dependent. Then you have some simple results regarding linear independence of vectors. You can use these in the problems. Any set containing zero vector is linearly independent. I explained you in the previous lecture. Infinite set independence means every finite subset of the set should be linearly independent. And today I have explained you basis of the vector space. Basis means any subset of the vector space which is linearly independent and spans the vector space. Such a set is basis. Standard basis you should keep in mind. For R2 it is 1 0 0 1. Sometimes we also write 1 0 as E1. E1 means 1 lies at the first place and second place is 0. E2 means 0 1. So what is standard basis for R2? E1 E2. For R3 E1 E2 E3. Just a shortcut notation. Okay. So how to check a given set is basis? You need to verify two things. The vectors in the given set are linearly independent, and secondly, any member of the vector space should be written as linear combination of the members of the given set. Or you can say the given set spans the vector space. So practice some problems, it's easy. Again, this is very important result. Number of elements in the basis of a vector space doesn't vary. Elements can vary, but number of elements doesn't vary. This leads to this key definition, dimension of a vector space. What is dimension? Number of elements in the basis of a vector space is called its dimension. So you find any basis of the vector space, count the number of elements in the basis, that gives the dimension. Okay. Dimension of R2 is 2, dimension of R3 is 3, dimension of M22 is 4, like that. After that, how to construct bases from a given set of vectors in the vector space. This is also important to know. If S is any given set, say V1, V2 and so on, Vn, in the vector space V, from this set we can construct bases of the vector space V. What are the results related to it? If S is spanning set, spanning means LS is V. In that case, how to construct basis? Find maximal linearly independent subset from it. That will give the basis. In case S is linearly independent, it is linearly independent, then either it is itself a basis, or you can add vectors from this result. You can add vectors, you can insert vectors in the set to form the basis. How many vectors are to be added? Equal to the how many vectors? So that total number of vectors in the given set is equal to the dimension of the vector space. For example, you are given R3 and some set is given, say 1, 3, 4. From this set you want to construct a basis, so it is independent. Now how many vectors are to be added to form it a basis? 2 more vectors, because dimension of R3 is 3. Okay. So we can construct basis from the given set. If it is spanning set, find maximal linearly independent subset from it, that will form basis. If it is linearly independent set, then if it is either if it is itself a basis, it's fine. Otherwise, insert some extra vectors to make it a basis. So these points I've already explained you today. From the basis, you cannot remove vectors, you cannot insert vectors. If you remove vectors, it loses the property of spanning set, and if you insert vectors, it loses the property of linearly independence. So number of elements in the basis remains same, that is called dimension of the vector space. After that, you have learned that if you have row equivalent matrix, then you get the basis from that also. So you can find RREF in case of R3, R4, etc. You can find RREF of the given set of vectors, and you can determine simplified span, or you can say another basis for the vector space. So hope all main points are clear to you. Thank you. We'll meet in the next lecture.